The row-reduced echelon form of the augmented matrix of a linear system gives you a lot of information about that linear system. So in this video, I just want to quickly review how to analyze a row-reduced echelon form. Suppose we have a linear system, such as this one, and we want to find the solution set. Then we convert that system into an augmented matrix, and then we used row reduction, so elementary row operations, to get to what we call the echelon form, the row-reduced echelon form attached to this system. For each row, the leftmost number that is non-zero is called a pivot. So here we have 3 pivots, and we see that the last row does not have a pivot. It is perfectly fine that the last row is all zeros, but it is actually very important here that there is no pivot in what we call the augmented column, because if there was a pivot there, if it was a row of zeros and then a non-zero number in the augmented column, it would mean that the system is inconsistent, meaning that there are no solutions. But since there is no such thing in the last row, it's a row of all zeros, there is no pivot in the augmented column, this system is consistent, so there are solutions. Now we have to decide if there are just one solution or infinitely many solutions. Some terminology here. The entire matrix is the augmented matrix, and without the last column is just the matrix of the system. Now, whether there is one solution or infinitely many solutions depends on the number of pivots in the matrix of the system without the augmented column. If there are as many pivots as there are columns in the matrix of the system, then the system will have exactly one solution. But if there are columns in the matrix of the system without pivots, then there will be infinitely many solutions. In this case, we have 2 different columns in the matrix without the augmented column that do not have pivots, and that means there are infinitely many solutions, and those 2 variables, in this case, these columns correspond to the variable u and v, are going to be what we call free variables. And finally, one can use the augmented matrix to come up with the solution set. We solve for x, y, and z in terms of the free variables u and v, and we get what it is, the solution set for this system.